Okay, so with this chapter, there are 3 tests. The hardest part, or I guess the largest thing to overcome, is deciding what type of test it is. And then the only difference in the write-ups are the hypotheses. The calculations, or assumptions, calculations, conclusions are all the same. So I'm going to take us through the hypotheses, and then from there, that'll we can finish up with a write-up of seeing what that looks like. So in a goodness of fit test, it is when you have 1 sample and 1 variable. Oh, I didn't put a degrees of freedom column. I got rid of that. Sorry. Expected value, degrees of freedom. So when you have 1 sample and 1 variable, typically when you just see a list, of data, you'll know that it's a goodness of fit. You have to calculate your expected value by hand, or your expected proportions, and you do that by taking n times p. So your sample size times your proportion. These go in list 2. So you're going to have to input them yourself into list 2 by hand. Now the proportion is either given to you in a ratio, like it gives it to you in the problem, or like the ones we saw in the homework, you assume that they're all the same. Like homicides are not more prevalent in one season than another. So I'm going to make all of the proportions the same, 0.25, 0.25, 0.25, 0.25. And then you're trying to prove that maybe one season is different. Yeah. Degrees of freedom, you take your categories minus 1. So K is just your categories. And then you subtract 1. The hypotheses for this, yes.
So on the back to that, what was that example with the education?
Mm-hmm.
So there's education levels, but that'd be 4 minus 1. Then?
Well, so whenever we get to homogeneity and independence, the formula changes.
That wasn't goodness of fit.
Yes. So for my null hypothesis, this is the only one where you're going to actually have numbers. So you're going to take all of your categories and you're going to list out the proportions. So I think that the one in the book was like the butterfly example, talking about, or the fruit flies. Do y'all remember that example? So P1 was 9 over 16. P2 was 3 over 16. And you do that all the way. Like you list out all of your categories and the proportions that they give you. Let's say that, the months or the seasons in the year and the homicides that occur, I think that was number 5 on your, or 3 or 4 on your homework, you would put 0.25 for all of them. Because the expected proportion is that each season of the year has 25% homicides. So that's what you expect to happen. So in your null hypothesis, these numbers are your expected proportions. They're your expected proportions. They're always decimals or fractions. Then you define what they are. So you say where P1, P2, P3, P4 represent the proportion of homicides in, and then I'm going to list out the categories. So I don't know how they were listed, but you would put them in order. So maybe winter, spring, summer, and fall, respectively. Respectively indicates that you're putting it in the right order. So 1 goes with winter, 2 goes with spring, 3 goes with summer, 4 goes with fall. Or you could list it out where you say, I'm going to erase this after, but P1 equals proportion in winter. And then you do P2 equals proportion in spring. P3 equals P4 equals. And you just list them all out separately. I don't really like doing that because it takes longer, but if you want to do it separately, that is okay as well. Then your alternative hypothesis is you say, so the HA is at least one proportion is different. And you write that verbatim. So the null is like you expect them all to be the same. The alternative is I'm trying to prove that one is different. So maybe I'm trying to prove that spring has more or summer has more. But just simply saying at least one proportion is different. For homogeneity, it is when you have 2 plus samples. They must be independent and random. So they must be independent. You only have one variable. Expected value, if you were doing it by hand, is you take row total times column total. Probably should have done my spacing better. Column total divided by grand total.
Is that something in?
Yes, like the total sample size. And it's the same for this. I'm going to just draw an arrow. Degrees of freedom, you take rows minus 1 times columns minus 1. It's like your total sample size, like out of everyone. Rows minus 1 times columns minus 1. So if I had, like I think in the example it had 3 views, like side, front, and then 3/4. So then if that's 3 categories, or 3 columns, then I'm going to take 3 minus 1, which is 2, and then I had men and women, so that was 2 samples, so then it would be 2 minus 1, which is 1. So 2 times 1 would give me 2 degrees of freedom. For the hypotheses, I'm going to erase this. I needed to plan better. For my hypotheses, there are no numbers in the next 2. So the null hypothesis is saying the true proportion of, and then you put in your context, is the same for, then you list all of your samples. So the true proportion of, I don't know, what's a good example? The true proportion of color distribution and M&Ms is the same for peanut M&Ms and plain M&Ms. The alternative is you say at least one proportion is different. So you're inserting context here and here. For independence, when you have one sample and you have 2 variables, the words that you will see are obviously independent, dependent, but you also might see the word association. You might see the word correlation. Those are all triggers to help you know. And then for homogeneity, it's going to have the word samples. So that S is an indication. Homogeneity and independence can be the same, like you can use the same data set but ask the question in a different way. So for instance, if I'm using plain and peanut M&Ms and I'm comparing the color, then that's multiple samples. I'm only looking at color, so that's one variable. If I have one big batch of plain and peanut all together, they're just in one big bowl, which is what we're going to do today. I take one big sample and I separate them by type and by color, then that gives me an independence. Like I would say, is there an association between type and color? So it's just how the question is worded and how the sample is taken. So the null hypothesis for this, you would say there is no association between X and Y, whatever that is. And then the alternative is that there is an association. So you're inserting context here and here. So out of the ho and the haw, which one is saying that they're independent? The ho. So the null hypothesis is that they're independent. You're trying to prove that they're dependent. So maybe there is a relationship between height and weight. Maybe there is a relationship between type of M&M and color. So we're going to look at this. We're going to decide. Already I have a table. So that's going to tell me in this two-way table it's either independence or homogeneity. So let's read and see what it's going to be. So it says that we took a sample of 450 undergrad students. One sample. So that tells me what? Independence. But if I keep reading, the problem says, is there evidence that there is an association between class standing and response to the body art question? That tells me that it's an independence test right off the bat. How could I have asked this in a homogeneity way? Or how could I have done the same thing but doing it with homogeneity? How could I have split the samples?
Based on like freshman sophomore.
So I could have taken 4 samples. And I could have said, is there a difference between the class standings? So I could have taken 4 samples and then just asked them about their, like whether they have a piercing, tattoo, both or none. So that's how you can see the difference between them. So let's start with our hypotheses. Ho and haw. The null hypothesis for independence is what?
There is no association.
There is no association between, what is my X and Y?
Class standing in response to the body art question. Other questions? Body.
The alternative?
There is.
Mm-hmm. Okay, next step is I want to put this data into a matrix. So once you finish writing that, go ahead and put this data into a matrix. Okay, so for assumptions, we did the hypotheses. For assumptions, there are 2. The first one is what?
Is there independent random?
You only say independent when there are multiple samples.
Oh,
So
wait.
in the independence and the goodness of fit, we just say there is a random sample of 450 undergrad students. The next thing I need to check is that my expected counts are greater than 5. So once you have your data in a matrix, the only way to check it, or I guess instead of doing them all by hand, a way to check it is by running the test. So I'm going to go to stat test C, stat test C. I'm going to leave observed and expected the way they are. I'm going to hit calculate. Then I'm going to go back into my matrix. So hit second matrix 2. Or you can even go to the edit tab and look inside matrix B. But once you click enter, it should give you the expected values. So I'm going to put them in parentheses out to the side. So 49.7, 37.9, 23.4, 34.0, and I'm just putting them in next to it. And I'm just going out one decimal place. Are these right? Sometimes going back into the edit tab makes it easier instead of trying to scroll.
Wait, what is stat test what?
C.
And what's that?
That runs your chi-square test. So once you run the test, then you can go back and see the expected values. But you have to run the test first.
Where does it show I have title, x squared, p value, df. Is it x matrix?
Go back into matrix 2, or matrix B. Okay, once you have these, you can say all expected counts are greater than 5. Then just say in parentheses next to observed. And then you could draw an arrow to them. Just make sure that the AP grader knows that you have expected counts somewhere.
Is this the x squared two-way test?
Mm-hmm.
You're supposed to do that?
The chi-square.
Oh, yes.
From there, the calculations, the name of the test is a chi-square independence test. So I'm going to do stat test C. My test statistic is 29.5. My p-value is 0.000532. I have 9 degrees of freedom, and my alpha is what? 0.01. Now, if you did want to write out the formula, some people like to do that. You don't want to do this a million times. So the formula is the sum of observed minus expected squared over expected. It's the sum of that. So my suggestion is do like maybe the first two plus ... the last one. And so, no, you do not have to write out the formula. But if you wanted to, some people like to, and I'm going to show you kind of what the formula looks like. So my observed would be 61 minus, what was the expected? It erased. 49 over 49.7 plus, maybe if I'm going across, 7 minus, what's the expected in that one? 15.1 over 15.1. And then if I wanted to do the last one, 54 minus what? 57.9 squared over 57.9. And that whole chi-square equals 29.5. So the reason why I show you this is because each individual cell gets inputted into this equation. So imagine doing this 16 times. Each one of these is called, or is what we call a contribution to the test statistic. And this word shows up a lot on multiple choice questions. A contribution is how much of the test statistic it consists or it contributes to it. So all of them added together get to 29.5. Sometimes a question will say which cell had the biggest contribution. Well, the first thing I'd want to look at is like which cell or which block has the largest difference between the observed and the expected. That's kind of where I'm going to start. Yeah, but if it were a multiple choice question, you would just do it 4 times. So basically you're putting it into the formula and then deciding which one's the biggest number. So the conclusion is, since the p-value is less than alpha, I reject HO. There is sufficient evidence to suggest, and then you just write the HA. So to suggest there is an association between class standing and response to body art question.